We have an unidentified flying object.
I'm Jack Oswald, and you're listening.
This is Neptune Hammer, and you're listening to...
I'm Richard C. Hoagland, and you're listening to...
I'm Art Bell, and you're listening to Dr. J Radio Live.
We have an unidentified flying object.
One, but my family's in that same work, no play, worry about bills, and then repeat same day. There's much more to life than that, and we have to obviously accept what we have learned from both extraterrestrials and visionaries. There are several visionaries I could think of: Leonardo da Vinci, Arthur C. Clarke. I even call Nassim Haramein a visionary for what he was able to discover. I remember when I booked him for Art Bell was using the first part of the show to say why didn't he have any training, from an institution, and nonetheless, of course, there was, on top of that, we definitely had. By the end of the show, he was so impressed he wanted him back, although he did require, nonetheless, we bring you someone that you have requested multiple times, and I was able to secure him for tonight. If you haven't checked out the social media, anywhere from Instagram, Twitter, Flickr, Tumblr, Google+, and Facebook. I believe those are just some of the sources. Everything is in the name. Don't forget that. Don't forget that everything is in the name. Nonetheless, what I would like everybody to do is, like I said, join the show by calling 818-923-1713 if you have a question. 818-923-1713, or use Skype. There's two Skype accounts you could use. One is Dr. J Radio Live. Remember, that is the same phrase as it has for everything, all social media accounts. DRJ Radio Live. The other Skype account which you could use is Skydiving Lawyer. Again, Skydiving Lawyer. I know they're very different, but they both lead to the same place. So now that I've already spoiled my guest, he's a physicist who's been on the show several times. You can read about him on resonance.is. And why does that name ring a bell for you? Because when Nassim was recently on, that's where he has his academy. And this is someone who we've had on the show a few times, and you guys truly enjoyed him. And I pondered some questions that I wanted to ask him, or any physicist, and he was up for the challenge and to tell us how it really is. So without further ado, I would like to introduce Dr. William Brown, PhD.
Thank you. It's great to be back on the show. Really looking forward to tonight's discussion.
It's always a pleasure to speak to you. Now, some of the things I told you I wanted to talk about before we can go in any realm that you want, and by all means, if you have anything that you want to say, don't hesitate to, divert the question or divert the answer to what you want to the audience to know. But some of the topics we talked about are string theory, and then you said how they view it, meaning the mainstream media, and how we view it at the Resonance Academy.
Yes.
And then, of course, just before the show, I asked you if we could also talk about singularity and big bangs. Now, let me give you a premise on why I got this interest all of a sudden. Obviously, from having about 450 guests on the show over the last 5 years, and then some because there was live interviews, I always understood that vibrations, and for instance, when Jim Sparks, the alien abductee, said that because they are from a different world, their vibrations are different, so that's why as the closer they get to you, the more things you feel, such as anxiety and even to the point of blacking out. And so I just assumed it, but I never quite realized what the science behind it was. And what I found in the Nova documentary, which is on PBS, is that it is based on string theory, which is our subatomic particles, essentially strings that could be bent, they could be, elongated, and there's trillions of shapes if you just have a small adjustment to them, and possibly even loop them around. Nonetheless, each of those is a vibration. They emit a vibration, and that's what made sense to me. So let's start with that first. I mean, is that what string theory comes down to?
Yeah, and actually, though, a couple of the things that you had said, like that there are, thousands, millions, and actually the number's so large that there isn't a word for it, the number of different potential conformations of these strings, the different kind of geometries that can be adopted. That's actually one of the biggest problems with string theory. And I can get into that a little bit more, why that's such a problem. But in terms of vibration, you don't need a string. We can understand that really well by analogy because, stringed instruments, when they vibrate, they produce very specific notes or even chords when you have numerous strings vibrating in a specific harmonic ratio. However, particles can vibrate, three-dimensional particles can vibrate. So it's not absolutely necessary that you have the concept of strings to explain something like the higher vibratory frequency of a particular object, or in this case even a being. It can be just that the subatomic matter that they're comprised of is vibrating at a much greater frequency. And certainly that is why oftentimes ships that are sighted and even the beings that come out of them will appear to glow. They will have light emanating from them. This is oftentimes because they are being translated from a plane of existence, an alternative reality, if you will, that the constitutive energy level is much, much higher than ours. And actually, this isn't like mainstream ideas at all. A mainstream scientist would be throwing tomatoes at me right now. But anyways, I'm okay with that. Even the process of going into what we perceive as the future, that's actually shifting to alternative realities. The future isn't some nebulous, unformed potentiality that is somehow ahead of us somewhere. It's there. It's here right now, past, present, and future. Time time is somewhat illusionary in that sense. And the process of moving into what we perceive as the future is an increase in the constitutive energy level of all matter. This causes an expansion of space, an expansion of even possibly the particles, matter, planets, beings expanding, growing, and they're at a higher energy level, such that if you were to travel back in time, which is possible, if you were to go back 200, 300, 400 years ago, you would appear to be slightly iridescent. You would appear to glow a little bit.
So you essentially glow as light beings, or even
exactly.
as the Shroud of Turin. When we interviewed the leading expert, he talked about that it was a luminous body.
Yes, yeah. So these beings, these figures that are oftentimes mentioned in esoteric or religious texts, they have halos, light beings, sun gods, glowing beings. Obviously one idea is that it's all just myth or whatever, but there's also actually on the logical side a possibility that they're time travelers. Interdimensional travelers.
Yes, I'm glad you mentioned that.
And so they have what appears to be magical abilities. It could be extremely high level technology. The ability to work with and manipulate the ether, space-time itself. And so they have phenomenal knowledge, wisdom. And so, they become godlike in our mythos, but yeah. So, and it doesn't, though, necessarily require, the strings. It's really, for me, the string theory is just unnecessary, and its basic premise. Its basic assumption is so flawed that I'm actually astounded that these advanced physicists, our peers, don't take issue with this, and I've been figuring it out why that is, and it's mostly because the physics community.
I'm Art Bell, and you're listening to Dr. J
Hold
Radio
on, sorry,
Live.
that was a mess up here. Who
Listening
did
to
that?
Dr. J Radio Live.
Who screwed that up? Okay, let's stop that. Sorry about that. Whoa.
No problem.
That's our break music. Obviously, our audio technician is looping around over there. We're going to give you some trouble, folks. Anyway, nonetheless, please continue, Dr. Brown.
Okay. Well, so the physics community has gone so far into the mathematics that, yes, technically they're physicists, but they're actually first and foremost mathematicians. Now, if you go back even 100 years ago or more, a lot of the physicists they weren't necessarily mathematicians. They would utilize mathematics, and as the theories got more and more advanced, it required more and more advanced mathematics. But Einstein, the quintessential example of a physicist, he required a great amount of assistance in formulating the mathematics, even of special relativity and general relativity theory. He on his own didn't actually have the mathematical acuity to formulate it on his own. But what you have now, and even in the last 40, 50 years, are mathematicians. And obviously they're brilliant. But
And let me say, mathematics are literally the language of the
Yes.
galaxy, universe, God, people say.
Yeah. But within reason. So and that's the thing. So the mathematicians, they have no problem whatsoever dealing with a one-dimensional object, a five-dimensional object, a 26-dimensional object, on paper, the math is no problem to them. They work in that abstract realm. But when you try to translate that to physical realism, and that's what it's called in the philosophy of science, the philosophy of physics is realism.
Realism. let me say this to you. Tom has a question for you and a reason for it. Go ahead, Tom.
Okay, here's something I'd like you to elaborate on. And that is, I've got this vague understanding. I don't have a good understanding. Maybe you can elaborate a little bit more about, two things. One, the concept of spooky action at a distance. And two, the other item where they were observing the mere observation, and correct me if I'm wrong, the mere observation of quantum particles was causing the observation itself was causing an effect to the experiment they were running. Can you elaborate on that?
Yeah, so you'll need to cut me off once we get about 45 minutes into this, because I'll keep going if you don't.
Yeah, but my understanding is weak, and I depend on guys like you to kind of interpret that.
Yeah. Well, so the spooky action at a distance is, a prime area of our focus, me and Nassim's work. And actually, it has a very strong correlation with the theories being developed in string theory right now. One of the hottest areas of string theory is called conformal field theory, anti-de Sitter space correspondence. It's the correspondence conjecture, and it takes string theory and holographic theory, and it brings them together. And it was actually this...
Okay, wait, Bill. Here's the question.
Okay.
The spooky exit at a distance, does this relate... No, I could be wrong on this. Okay. Does this relate to the possibility of us actually understanding how the transporter concept works, traveling across space? Is that part of that?
Yes, absolutely. Because... spooky action at a distance, it's showing what is called technically non-locality. So that you think classically, that conventionally, that in order for one object to interact with another object, they must be in proximity to each other, and there must be some kind of physical messenger, some propagating the signal between them that causes some kind of interaction. And you get evolution and development of those systems that are correlated together in that way through a physical interaction. That's locality. And classically, that was the only kind of action that was allowed. And in fact, when Newton formulated the theory of gravity, at that time it's a theory, the scientists of his day ridiculed him because he was postulating here that matter reaches out across space and interacts through some kind of mysterious force, and he was ridiculed for that. And nowadays we're like, the theory of gravity, the law of gravity, nothing could be more foundational, more self-evident than that. But in his day, that was kind of a non-locality, a kind of spooky action at a distance, and it was one of the reasons that his work in that regards was initially ridiculed by the scientific community. So now, though, with very sophisticated experiments in optical experiments using photons, and actually even other systems, macroscopic systems, they have quantum entangled diamonds, large objects together. But it's been demonstrated that there is some kind of non-local interaction or correlation between objects. So irregardless of the spatial separation, irregardless of the temporal, how far apart they are in time, they will have a correlation in their behavior. Their behaviors are not independent of each other. Now, this was problematic because classically there has to be some kind of physical transfer of information, really, in order for there to be some kind of correlation of behavior. But these can be farther away than a light signal can transfer between them and still have some kind of correlation of their behavior. So unless they're transferring information superluminally or faster than the speed of light, there's some unforeseen way in which they are behaving as if they're right next to each other. Now, so there's many ideas for this. And so, in fact, this was given by Einstein, Podolsky, and Rosen in a paper in the 1940s to demonstrate why quantum mechanics was wrong. It's called the EPR correlation. And that is when Einstein famously said, spooky action at a distance. What is really ironic about that is that one of the solutions to this seeming paradox is through another piece of work that group did at that time called Einstein-Rosen bridges. What we know today is wormholes. This ties back in again to string theory, but what they were doing, they were trying to resolve singularities. So there was a number of different singularities at that time. One was a geometric gravitational singularity known as a black hole. Another was in the quantum realm, point particles. Point particles were singularities.
Can you explain what the singularity is within a black hole?
Yeah. Well, this is
because I heard in the movie Interstellar that something along the lines of if they made they compared it to something. One of the scientists told the actor Matthew McConaughey that if a black hole is an oyster, the singularity is the pearl inside. Mm-hmm. But you couldn't see it, obviously, because of the gravitational pull and also the extreme gravitational pull, as well as the darkness. I guess the void. Can you explain that a little?
And it's interesting that actually this is one of the areas you want to discuss, because it's actually central. It's key to the entire issue. Mm-hmm. It's central to string theory, the development of string theory, and quantum mechanics. It's central to understanding theories within general relativity and cosmogenesis, the birth of universes. But the singularity is an extremely abstract concept. As it is conventionally applied, it is a region of zero dimension, a point. So, within the conventional mathematics, a point has zero dimension. You can't move left, you can't move right, you can't move up, down. There's no translation across space. There's no space, it's a point. Now, a one dimension would be a line, a string. You can move left and right. This is where we're getting into string theory. Now,
I'm actually already have a question, another question here. This is from... where is it? Let's see if I can get it right. Okay, it is two of them. Wow. Okay, Shari Johnson in Ventura. What comments does he have on the possibility of the ninth planet? That's one. The second one is from Adam Scott in Thousand Oaks, California. What does he think is causing the effects of KIC 8462852, whichever that means?
Okay. Yeah, so, the ninth planet, I'm a little bit biased. I'm a little bit partial on this because I was born where the original ninth planet was discovered. So for me, Pluto was always the ninth planet, and, I had a little bit of hometown enthusiasm for that. I saw the original plates that were first where Pluto was first discovered. But okay, so it's not a planet. All right, whatever kind of arbitrary.
Talking about KC, that one, right?
Well, no. So KIC,
the ninth one.
Yeah. Well, KIC that is a star that apparently is something different. That is a star discovered by the Kepler Space Telescope that appears to have an alien megastructure producing an abnormal spectral signature of the star. That's extremely interesting, and I can get into that. Now, on the ninth planet, the evidence for it is good. Although it is speculative.
Yeah. See, I just heard about it from this question. It's the first
okay.
time I actually even heard about this ninth planet.
Yeah, it's a very odd kind of situation because calling it a planet is, in my mind, actually stretching what you would consider the definition of a planet to be, because this object, much larger than Earth, but it has a 20,000 year orbital period, so that brings it out past the Kuiper belt, the solar system. So I mean, this is 200 times farther out than the Earth's orbit as compared to the Sun. But with some of these Kuiper belt objects, I think Sedna, Eros, and these large Pluto-sized, planet-sized objects, they have these, again, really interesting patterns where it's like they're all aligned, and the probability of that occurring by pure chance is extremely small. So it does appear that a good explanation is that there's a large object out there that is hurting these Kuiper belt objects, giving them this distinctive pattern. So I don't know. I mean, it'll be interesting to see, until they can get a picture of it, though. I'll need
Proof.
more proof. Yeah, more evidence. What they have is good. But the KIC, I forget the entire sequence of the numbers, but that was a very interesting development because. This is the Kepler Space Telescope.
Yes.
Which has identified over 5,000
exoplanets.
Yeah.
The Goldilocks planets, right?
Because
exoplanets, it's far more than 5,000. Goldilocks meaning that they're possibly close to Earth.
Close to Earth size. I think that they're only in the realm of 50 to 100.
Yeah, I heard about 100. Yeah. Earth-like? Oh, really?
Earth-like, yeah. Because those are by far the hardest to spot.
Yes.
But when you run the numbers, the calculation comes out that there's billions of Earth-like planets in our galaxy.
Who even says we have to have the same conditions to be living?
Yeah.
We even have proof of that on Earth. We thought you couldn't live without light. Then all of a sudden you see heat fissures in the deepest parts of the ocean with life thriving on it.
Yeah. Oh, yeah. Yeah, it's an extremely conservative viewpoint. I'm really optimistic that we'll find life on Europa. In the moons of Jupiter, the Galilean satellites. And Titan is like a little pre-biological factory. It's producing tons and tons of organic molecules that probably someday will be incorporated into living systems. They're probably the preconditions that gave rise to the life on Earth, the matter, the organic material for life on Earth, probably came from a system very similar to um, Titan. And it has lakes of methane. The ice, the water is frozen so solid that it's a rock. But it has oceans of hydrocarbon material, liquid. Very interesting place. So yeah, I mean, the idea that it has to be in this particular temperature range, and on this particular size body planet, is extremely conservative, narrow-minded view, really. But I mean, even within that narrow range, you have billions and billions of Earth-like planets in our galaxy alone. It's like, it's the folks who are talking about, extraterrestrial life, other life in the galaxy, aren't sounding so crazy anymore.
That's right.
Yeah.
You know that as well as I do. When we were both young in school, we were taught that the only solar system in the universe was ours.
Yeah.
The galaxy was nothing but space dust and stars and supernovas and all the other anything related to a star, and that's it. We were very unique. And then, of course, our planet was even more unique because it had us, and all the other ones were just empty. But now things have changed. Anybody who's 21 or older, 22 actually or older now, started kindergarten when they were teaching them that exoplanets have been found.
It just blows my mind how people can be that myopic that they would question whether there's other planets in the galaxy. But the idea that this would be it in the entire universe. But it goes on today. People questioning serious scientific discourses, serious scientific discussions on that this might be the only place in the universe where there's life. And it boggles my mind how somebody could suggest that. I mean, it's not outside of the realm of possibility, but it's just inane, I think. But so I wonder how long before, just like the discovery of extra solar planets, and I don't think it's going to be too far off that we'll have, indisputable proof of life beyond Earth. There's already been pretty good discoveries. I mean, the Murchison meteorite, there was one even found more recently that had telltale bacterial and even cyanoflagellate organisms in it. So it may have already even been discovered. It's not accepted, but
yeah, I was referring to also because they were saying that about Mars, that where there's water, it's a good chance of it, and microbes in the ice, the polar caps, something along those lines. It was Richard C. Hoagland told me this.
Yeah. So, underneath the surface, so even on Earth, there's living organisms.
Underneath?
Yeah, 2 miles underneath the surface of the Earth. I mean, way down there, under extreme pressure, oftentimes extreme temperatures. The kind of organic material, I mean, they're living off of chemical reactions with the mineral compounds down there. So in the water they get, it's difficult to get water down there and rock under that kind of pressure and temperature. So under the surface of Mars, I mean, we've seen liquid water pouring out. It's quite possible that there's living organisms there. And the Voyager probes in the 1970s, the tests they did for organic material were positive.
Interesting, really.
Yeah.
And you're talking about probes just to Mars or other planets as well?
No, just on Mars. There was. I think I'm sorry, the Viking landers. They when they touched down, they had a little organic chemistry set on there, and they did some basic type reactions that would identify organic compounds in the soil, and those tests were positive. But and this is where it gets into kind of like some Hoagland type area, because there was this huge campaign to discredit it. Why did they why were they so fierce in discrediting?
I know. It blows my mind. We have a caller, Wendy, who hosts Granada Forum, just called. Wendy, welcome to the show. Do you have any questions for Dr. William Brown?
Yeah. Well, first of all, Dr. J, thank you for taking my call. And,
Always.
And thank you, Mr. Brown.
Yes.
I was wondering last night, in the news and even on George Nori, they mentioned about this new planet they have orbiting in it. They don't.
Yeah,
we
just discussed that.
Yeah, they just said we don't have a picture of it, but we know it's there. Isn't that planet Nibiru that people have been seeing all over the world, and they put it up on the websites that they've really been ignoring on the major mainstream news, especially because it's really heavy on the internet.
Mm-hmm. And if there was ever a candidate for Nibiru, this would be it. Of course, I don't know, the calculations that they've done on its orbital path through the solar system doesn't bring it anywhere near to the inner solar system. But, I mean, they're at the most earliest stages of even identifying this planet, if they even have done so. But I mean, its 20,000-year orbital period makes it a prime candidate for a Nibiru-like object, especially the mass and size that they've calculated for it. It's a possibility,
Yeah. I know there's lots of different pictures on the internet, and like one shot from Florida where a person just happened to catch a sunset, but it was just perfect because you can see the planet. You see the sun, and you can actually see the planet, and the moon is somewhere else in the shot. So there's three there's three of the one. So it's kind of a cool shot. You know what I mean? So it's good. But and another thing too. I know this sounds weird, but. Okay, they talk about they degraded Pluto as a planet. I mean, isn't that kind of stupid? I mean, since it was born, it's always been named Pluto. Oh, but we don't like you. We're going to degrade you. You're no longer a planet. There's something wrong with that.
Yeah. It is.
And weren't they considering to make it a planet again? So they decommissioned it as a planet, and then so all of a sudden we had 8 planets instead of 9 planets in this atmosphere or the solar system. But aren't they even reconsidering it, Dr. Brown?
Well, there's a number of individuals, astronomers and other scientists who are strongly disputing that move to redefine it as a planetoid or a dwarf planet, to knock it out of its normal status, because for one, it is extremely politically motivated, and the process of redefining it was purely arbitrary. It was like not based on any kind of logical, like scientific type methodology that you would normally apply to defining something. It was just pulled out of a hat, on how they were going to redefine what a planet was. And actually that arbitrary nature of it really has been a source of contention for a lot of people. But, the political motivation for it was the planets that they have been finding in the Kuiper Belt object. they didn't want to add these objects to the count, the planet count. I think we'd probably be at 12, almost 13 now, if they were including these other objects. And so, the Kuiper Belt has now become this, supposed trash bin of the solar system. All the leftover junk is out there, which is just ridiculous. It's erroneous in the extreme sense. But Pluto does have some, characteristics that make it questionable to call it a planet. I mean, it is a very small object, relatively speaking. It's smaller than our moon. So it has a highly, eccentric orbit. But I really disagree with demoting it and saying it's not a planet. I think it's kind of ridiculous, especially the latest images that they got from it. I mean, it has active geological events occurring on its surface. It has a very complex surface. There's it's far more complex than our moon, certainly. In 3 orbiting moons of its own. It's a very dynamic object. I mean, it's not something to be dismissed.
We actually have. Thank you so much, Wendy, for calling in. And you can plug in your show. She's on tomorrow night, or Friday night, same time. Yeah, tomorrow at freedomslips.com Studio A. It's called Granada Forum. Thanks again so much, Wendy. Johnny Webb in London has a written question for you. Go ahead, Johnny.
Hey, good evening, William. Good evening, Dr. J. The first question's coming in from Facebook, from Jerry in Plymouth in England. And he's asking, in the movie Close Encounters, Richard Dreyfuss, the actor, leaves in a UFO as an off-world officer. And he asks, where do you think they were going off-world?
Myself, I think that they're in for a little interdimensional journey. These kind of technological capabilities to travel through space at the distances to where you could get anywhere of significance. For one, it necessarily means that you're traveling through time. There's no way around that. So, they at that point were time travelers. And the time travel gets extremely interesting. Especially, even just going at a significant fraction of the speed of light relative to the Earth, you travel pretty far into the future. You can go pretty good distances in short amounts of time. But I don't think that these craft, these beings, it's probably a diverse number of them.
Yes, that's right. That's been shown, at least. One of the participators who in Crash and Retrievals, Clifford Stone, in the Disclosure Project 2001, said that when he had left the Army in 1989, the Army had cataloged 57 different types of beings.
Wow.
Yeah.
Wow. It's and I kind of go, yeah.
What was also interesting, William, is in that movie Close Encounters, from my understanding, is there was a French guy that was running the whole show, and I believe there's a real gentleman that's alive today, Jacques Vallée or something.
Yeah. He passed away, but Jacques Vallée was real in the movie.
Wow. I gotta wonder what kind of experiences they were having that would, lend them to creating, such a movie. It's really, I think, exercises the imagination. But it's I'm fairly certain though that what you're talking about is, in a sense, interdimensional travel, so that not only can you go to different points from our perspective in time, but very quick trips to different realities, different planes of existence. It gets weird. It's not as straightforward as one would think, but.
Well, nonetheless, we have a little under 15 minutes before the break. About that. And I want to go back to what we were originally talking about. Okay, answer this question for me. The Big Bang. Do you believe it's possible that it's been infinite? Is that what singularity is? That there was a Big Bang before that, and a Big Bang is probably still occurring now and creating all these dimensions?
Well, I have to, explain the singularity because although it is conventionally defined as a point of zero dimension, I don't believe.
Interesting, really.
Yeah,
So it has obviously a dimension would be our length, width, height, or in time, right? That's the fourth dimension. But so a zero dimension?
Yes.
That blows my mind.
Well, and so the thing is that I don't think that those have real physical reality. Now. Maybe in some sense they must, because, if you can imagine something, and certainly if you can write the mathematics for it, in some way it must have some kind of existence. I don't know exactly what that would be, but the idea of actual singularities is wrong. In fact, I believe. And if you look at the assumptions and the thinking behind them, it's erroneous, it's illogical. The reasons why they're coming to these singularities. In the case of these geometric or gravitational singularities, the idea is that there's so much mass and so much energy in a small area of space that it will collapse down into infinite density in zero dimension. There's your singularity. Now, the reason these have been such mysterious and even magical objects is that that has been the cutoff point for science, because an object that collapses down to that size it's a subatomic particle. You're now talking about an area that requires a quantum mechanical description. So you're taking a supermassive star, for instance, something 100 times the size of our sun, and you're collapsing it down into the size of a proton. Now, normally, what they do in general relativity, since they don't have a quantum mechanical description for that, is they say, it just keeps on collapsing down, infinite density, zero dimension. But we've gone beyond that. We have quantum gravitational solutions. We know how objects with that kind of gravitational force behave in the quantum realm. And so, for instance, an object with 100 solar masses that is collapsing down to the size of a proton, it's going to reach a point of quantum gravitational repulsion, a repulsive pressure. This is related to the Planck density, which is actually the 0-point energy density of the vacuum, 10 to the 96 grams per centimeter cubed, or 111 joules per centimeter cubed, an extremely high amount of energy. That's orders and orders of magnitude more than the energy content of the universe, as far as its extant matter goes. So you never reach something of zero dimension. It remains three-dimensional. However, where it gets interesting again is that what Einstein and Rosen were doing, so they've got these singularities because it's occurring with your gravity, your geometrical objects, but they did it with subatomic particles also. Your electron, in fact, all leptons, which includes quarks, which make up supposedly your protons, these all became objects of zero dimension. To this day, you will hear the standard model of particle physics talk about them as point particles. And when they say that, what they mean is these objects have zero dimension. It's completely divergent from any kind of reality. And, I just chalk it up that they're mathematicians, and so they don't care about that, But the problem is that something with zero dimension has no internal structure. So it can't have any kind of structure or mechanisms that give it its own mass. They give it its own charge, its own magnetic moment. So all of these observable characteristics have to come from somewhere else with a point particle. And that's where you get things like the Higgs boson, which is bogus, W and Z bosons, which are bogus, and the idea of quantum spin, that an electron or a quark has spin, but it's not really spinning because it has no dimension. It's a point particle. So this spin is just some kind of magic intrinsic characteristic that gives it a magnetic moment and produces magnetism. And so their solution, one of the solutions was, well, okay, let's make them one-dimensional objects, strings. So you go from zero dimension, you make them a one-dimensional object. Now you can give it some kind of property. It can actually have internal structure, some kind of dynamic. It can vibrate up and down. And now you can say, oh, this vibration gives it its mass. This vibration gives it its electrical and magnetic moment. I've got an even crazier idea. What if you made them three-dimensional objects and they actually contain energy and matter, and that's what gives them mass and some of their other properties. And they're actually spinning, and that produces a magnetic moment. So that's kind of where I take issue with string theory. Not that I'm saying it's completely wrong. I might, in 5 years' time, come back and be a strong proponent of string theory. But that's where I'm at right now. Now, this is very much related to your gravitational singularity of general relativity. Your black hole, as it turns out. So
yeah, the Einstein-Rosen bridge.
Yeah. So they're looking at singularities. They're trying to resolve this issue of the infinite self-energy that you get with a point particle in quantum mechanics, the electron, the positron, the quark, and the breakdown in the description of a gravitational singularity, your black hole. Well, they kind of had the same solution as string theorists 20, 30 years later. What they found was that these objects do extend through space. And when you look at the geometrical extension of them through space-time, it's a bridge, a wormhole. An Einstein-Rosen bridge.
Yes.
So it's called maximally extended black holes. So, for one thing, any black hole now becomes immediately a wormhole as well. Now, you take it a little bit further. Okay, you've got the same problem with your subatomic particles. Well, what if they're black holes? What if they're wormholes? This is called quantum geometrodynamics, and it was developed by John Archibald Wheeler, continuing the work of Einstein and other geniuses. And he developed the Wheeler wormhole, and what you found was that he could produce he could describe the mass of particles, the electrical charge, the magnetic moment, all through the spin and wormhole architecture that they weave through space-time. So the electrical moment, you have the electric field, which is everywhere all the time. The electromagnetic field is always there. So you have electrical field lines going into one mouth of the wormhole and coming out another mouth. These are particles. So it's coming in one and going out the other. Well, if you're at one of those particles, you're only seeing the tail end, so it looks like it's just a positive charge. The other end of the wormhole, you're only seeing the head end. It looks like a negative charge. Lo and behold, you have your electron and your positron, which are just a wormhole pair. Now, so, this amazing description. Now, I hope I'm not putting people to sleep at this point. I told you you'd have to stop me on this.
Don't worry,
okay.
I'm enjoying this. This is why I brought you on.
Okay, cool. Because I'm giving you the lowdown.
Of course. We might have to take a break in a couple minutes, and we'll continue after. But please keep going.
You're not going to get this anywhere else. Okay, so now going back to developments in string theory, where they merged quantum or conformal field theory with
conformal field theory.
Yeah, and it's a jargon, highly jargon laden term, and it has to do with using anti-de Sitter space, another term probably hardly anybody's familiar with, to explain quantum field theory, so you can describe particles in a higher dimensional space. And so, in string theory, your strings become membranes, two-dimensional objects. And then they go to even higher dimensional spaces, and, they actually regain that three-dimensional architecture.
Would you say that these brains which make up string theory, or strings of the string theory, are what cause vibrations for everyone?
No, because it's a very interesting idea, but you gotta see how they're describing it. In our space-time, they're just strings, and
Gotcha.
they're using a mathematical space that's a higher dimensional space where they become brain-like, and that's just kind of for utilization. There's very few who actually think that there's any reality to that. But the vibration, a three-dimensional particle can vibrate just as well as a string can.
Yes.
And in fact, because they're so small, it actually becomes a pretty good approximation to describe it as a string. But, where I take issue is that it's not literally a one-dimensional object. I mean, what kind of reality is that explaining?
Yes. I mean, that's right. Well, what could it be if it's one dimension? Because it couldn't look like a worm or anything like that.
No,
but
anything you ever experience has three-dimensional structure to it,
At minimum, yes.
Yeah.
And that's one thing I want to get to after break is the people talk about 11 dimensions and so much more. Everybody stay tuned. We'll be right back with much, much more from Dr. William Brown, who works at the Resonance Institute, and he was a guest who has been on the show several times and, of course, was asked for a return by you, the listeners. We hope you're all enjoying, and just hear a couple friends as we go into a break.
I'm Art Bell, and you're listening to Dr. J Radio Live.
I'm Tony Gosling, investigative journalist from Bristol, England, former BBC journalist on BBC Radio. And you're listening to Dr. J Radio Live.
I'm Darlene Hooley, former Congresswoman, and you are listening to Dr. J Radio Live.
Hello, my name is Dan Sheehan. You are listening to Dr. J Radio Live.
Welcome back to Hour 2 of Dr. J Radio Live. As you heard, several friends and guests. Every single person has been a guest of this show, and they are very nice people, and each and every person that I book on this show, again, is brought by you, the listener, and is people that I appreciate and have always wanted to ask questions of. As you know, we've been speaking to Dr. William Brown, who works at the Resonance Institute. He is a physicist explaining some theories and topics that I've always wanted to be explained by, and this is the top authority that I know that could do such a job. Dr. Brown, if you don't mind, why don't you give some information on where people can get your material or find you other than resonance.com or IS?
Excellent. Oh, thank you. I'm glad you brought that up. So I have a personal website, williambrownsscienceoflife.com, williambrownsscienceoflife.com. It's all one word. And I have some material on there. I've been trying to incorporate more videos and stuff like that to make it a little more interesting or user-friendly. But there's articles on there, original articles on discussing various things. Now, on there, I have a link that actually comes from the Resonance Academy, which, I'm a faculty member there. I helped write and develop the curriculum for the Resonance Academy, but I recently did a lecture for our Channel 64 event. I have it linked through my website as well, but you can find it on resonanceacademy.is. And it is about almost a 2-hour long talk. I answer questions at the end, and but it goes over a good amount of what we're discussing now. And I start off, in fact, discussing cosmogenesis, so the birth of the universe, or how Big Bangs, as they're called, are occurring all the time. That kind of idea.
Yes, that was something actually we talked about.
Yeah.
I was asking you. Keep going.
Yeah. It's a pretty good discussion, and that's available for free. If you go through the Resonance Academy, they might want you to register, but I think it's still free. But it's kind of there to get your interest in perhaps checking out the program, the courses we have, because we've got a lot of material coming out through there. There's a guy, Jonathan, I believe Jonathan Weaver. I hope I'm not getting his last name wrong, but he's from New Zealand. He does a lot of really fascinating work with sacred geometry.
Nice.
Yeah, sure.
And isn't it true that everything comes down to sacred geometry, meaning that every single thing, including the atom, the earth, the way the world works, the galaxy, the universe, is all the torus, and it all involves a double tetrahedron?
Yeah. Well, so the double tetrahedron, which actually, though, is a triangulation of the overlapping three-dimensional spheres of the flower of life pattern, tessellation pattern. So actually, if you were to go to the root, it would probably be more appropriate to identify that flower of life pattern in 3 dimensions, where essentially you have overlapping 3-dimensional spheres, and if you connect the points where they overlap, and you do planes from those, you get tetrahedron, and then of course in the full pattern you get double tetrahedron, and then going out you'll get cuboctahedron, then the 64 tetrahedron grid, and on and on. So that, and Nassim has done core pivotal work showing how that is the fundamental geometry of the vacuum structure, that 0-point energy field, space-time itself. He uses that geometry and that pattern to derive or even predict the proton radius. He calculates its mass using that geometry, and calculates the strong nuclear confinement force as just an action of quantum gravity. So this is part of unification of physics, because he's showing, for one, how gravity emerges as a function of electromagnetism. So it all comes back to light, and the particle is just this pattern of light, this sacred geometrical pattern of light, that's the vacuum, and that gives you your quantum gravitational action, which causes nuclides to bind in the nucleus of the atom, and electrons to orbit the nucleus, or bind the nucleus, and so unification of the fundamental forces, and then cohesive description of their function. But one of the key things, though, so you've got that sacred geometrical pattern, the flower of life and the 64 tetrahedron grid. But from the flower of life, you can get the phi ratio, and so you have the phi ratio coming out of it, the golden mean. Now, that's an irrational number, and because it's not a single number, it's a ratio, a mean. So it has a constant variation. And in fact, this is very important because that's where you get asymmetry, among other things. And that is the other piece of the equation. So, you have the exquisite symmetry of sacred geometry, but one of the key sacred geometrical objects, the phi spiral, which you see the phi ratio throughout the living world, and indeed even the supposed inanimate world, but that's where you get the asymmetry, and that's the element that you need. Variability, variation, and that is the key spice of of the universe. Actually, without it, you don't have anything complex. You don't have living things as we identify them, certainly. It's that asymmetry. And for me, that's where it gets interesting because, you get into chaos.
Chaos theory, yes.
Yeah,
that is another topic of favorite of mine. We have actually questions from both people here, my co-host and, of course, my Tom. Tom has been waiting for a while, so I'm going to ask Tom to go first, and then, of course, Johnny Webb in London, it is now 4:11 a.m. Greenwich Mean Time. Yeah.
There's a trooper.
Yeah, he is.
All right, Bill, you there? Yeah, hey, listen, one of the things I like about what you guys are doing with Resonance is you guys are kind of bringing a new excitement to the whole educational process of getting involved in Resonance and with the Resonance project. You guys have made it exciting and really engaging, because I look at a lot of the posts that I see on the net, on Facebook and whatnot, and you guys are really making it interesting. One of the things I like is when people make a parable out of science to explain science. And somebody suggested I check out a movie recently, which I wasn't really going to check out. I wasn't really interested. So I got to ask you, did you see that movie? And if you haven't seen it, it relates exactly to this whole conversation. But have you seen that movie Ant-Man?
Oh, no. I actually, sad to say, I haven't seen it. I would not have thought that would relate.
I did not think it had anything to do with this, and I said, okay, I don't know if I want to watch this or not, but if you're interested in quantum mechanics, that's what the whole movie's about. This guy goes subatomic, he goes down below to the Planck level. It's actually very interesting, so if you get a chance to see it, it's very interesting in that regard. It's a parable about the ability to do that, and obviously we haven't figured out how to do that, but in this movie they do, and so it's really, like I say, it's a parable that explains to the layman a lot of what you're talking about. So I thought I might ask you about that.
Oh, that's very cool. Well, I wasn't planning on watching it, but I will now. Very, very interesting.
All right, Johnny actually has questions. Go ahead, Johnny.
It's another Facebook question from Joseph in Berlin, and he's asking, what do you know about the 11 dimensions that scientists are now seeing?
Yeah, so this is a very, again, interesting area. And, I have to go back to the historical development of these ideas, because then you can see where these assumptions are entering into the field and how these assumptions are erroneous. They're weird. I mean, I know that's not the greatest term, because weird things are okay, but I mean, they're illogical. I don't see the logic behind them. Maybe I'm the one that's at fault, but here's my situation, my contention with it. I was discussing Newton, who described gravity. Well, the thing is, he didn't actually describe the gravitational force. I mean, he showed the mathematics for how, the force will influence mutually objects across space, but there's no discussion, no treatment of how the force is actually created. How do bodies actually create a gravitational force? That didn't come along until Einstein. And
I'm Art Bell, and you're listening to Dr. J Radio
Whoa, sorry about
Live.
that. There's another technician there. Let's fix that real quick. What is playing those? Tom, I hope that didn't come with you. But nonetheless, we're back on. Sorry, go on, Tom.
Okay.
Dr. Brown, sorry about that.
And so Einstein has the brilliant application where, well, gravity, what's causing it, is that these objects, the material, the matter, is causing a geometrical deformation, a geometrical perturbation or change in the geometry of space-time. So, we can think of space-time as a coordinate system, and, normally it's just the same, and if you throw something through it, it goes in a straight line, and of course with inertia, it keeps going forever. But what gravity does is it changes, it bends all those coordinates and curves them. So now, if you throw something that doesn't keep going in a straight line, it curves into whatever is bending that the space. So he understood it as a geometrical change in the structure of space-time itself. So here was this brilliant description of where gravity comes from, what it is, how it works, and it was observationally verified, which made Einstein a kind of a rock star, because they were able to see a star that was behind the sun. They could see it because the sun bent the light around it. So even though the star was physically behind the sun, you could see it because it was being lensed around the sun. And this is an interesting effect, the lensing effect of space-time itself, because they use it as a cosmological sized telescope. If you have a quasar out 12 billion light years away, or even a galaxy out there, it'll bend the light and lens it so that you get just like a telescopic lens amplification of the light of objects that are behind it. So they can use galaxies and quasars as telescopes, because of this phenomenon. So it's real. It happens. Now the thing is that what about electromagnetism, our other main force? How can we explain it? Where does it come from? Well, what if you could explain it in the same way as gravity, as a bending of dimension? And this is where it gets weird, I think, because they go, well, gravity is already bending space, so what are we going to have electromagnetism bend to produce its force? And for some reason, it's thought that you have to have an extra dimension, so that the electromagnetism is becoming a force by bending this extra dimension that we don't see, because our normal three-dimensional space is all used up. Gravity's already bending it. Now this is where I don't get it, because you want to unify electromagnetism with gravity and show that they're one and the same force, and yet at the very beginning, the very outset, you treat them as two separate forces. What if it really is one and the same force? The same way that gravity bends space-time, electromagnetism bends space-time. But it was that unification process that caused them to the first application of a fifth dimension. and this was called the Kaluza-Klein theory.
Now, the movie Interstellar, I don't want to get too far into this because I know Johnny's got a couple of questions, but the movie Interstellar, you saw that, right?
Oh, yeah.
Do you remember when they showed what the fourth dimension would look like to a fifth dimensional being?
Yeah. And you know, I mean, it's interesting. You know, where you know, from a fifth dimension, you know, all of a sudden, time becomes like a spatial dimension, and you know that's interesting because I mean the mathematics do suggest that when you cross the event horizon of a black hole, your wormhole, the time and spatial coordinate, one of the spatial coordinates and the time coordinate, they flip in the mathematics, such that one of your spatial dimensions becomes time-like, so that you can move through it, but your time dimension becomes space-like. So now, you know, when you move, if you move left or right, you're moving forward or backwards in time. And this is a really interesting idea because wormholes and even black holes, which are wormholes, allow for the movement backwards and forwards in time. You know, it's very likely it's because you're moving through time as a spatial dimension.
Real quick, Johnny Webb has some questions for you. Go ahead, Johnny.
We got a question on Facebook again. It's from Jose, is it? Jose from Guatemala. He asks, what's on the other side of a black hole, and is it part of the chaos theory?
So, on the other side of a black hole, it might depend on what kind of black hole we're talking about. But because we're inside of a black hole right now, there's no question about that. If you take the radius of the observable universe and plug in the mass of the observable universe, it's within what's called the Schwarzschild limit, which is the technical definition of a black hole. So, you know, if you were to go across that event horizon, in some instances you might find yourself in another universe, parallel reality. Now, in a sense, we're always moving across an event horizon, and we call that time, because just like the light-like boundary of a gravitational horizon of a black hole, only it restricts your movement. You can't move. If you cross that threshold, you can't get out. You can't move in the y direction. You know, that's restricted. Well, we have time horizons as well, where it appears that we can only move in one direction, forward in time. Mm-hmm. You know, there's this kind of like time horizon where we can't move backwards. Now, if you would go again to a parallel reality, which is the past or the future, you know, parallel coexisting reality. So, you know, we're moving across horizons all the time. But
while you're on sort of time there, I do have another Facebook that's asking the same question, and it's from Maria in Paris, and she says, how does gravity affect time?
Yeah, so it gets extremely interesting. These are some weird results. I think that might be my buzzword for the but anyways, because gravity actually, since it is a change in the geometry of space-time, time moves differently because of gravity. So objects move differently. You know, whereas normally if you throw something without gravity, without this geometrical curvature of space. It would just go in a straight line and keep going in a straight line. But with gravity, it accelerates in the direction of the curvature. In our experience, it falls towards Earth, as we call it. But to its perspective, it's just moving in a straight line. But it looks like it's falling towards Earth, accelerating towards Earth. But what that change in the geometry of space-time will cause time to either slow down, in the case of strong curvature, or accelerate if you are moving away from strong curvature. And this has very profound effects in strong gravitational fields. For instance, around the event horizon of a black hole, because the closer you get to the event horizon, to the perspective of other reference frames of the universe, you are accelerating faster and faster, like you're going towards the speed of light, just by approaching the event horizon. And what will occur is you get a instantaneous one-way trip to the end of time relative to other frames of reference that don't have that kind of curvature. Now, essentially, you get to experience what it's like to be a photon, to be a ray of light, because for a photon, there is, in a sense, no time. There's no space for a photon because it's moving at the speed of light. Now, when you have that kind of acceleration, that kind of velocity, you get the same effect as a strong gravitational curvature. So, from a photon's perspective, when you look up at a star, when you look at Regulus, to the photon's perspective, your eye is touching Regulus. There's no space separation between it at all. And it takes no time at all for that photon to go from the surface of that star to the rods and cones in your eye. And in fact, this is one of the reasons why it is the connected universe. Yes. Because, in many instances,
or connected universes?
Thank you. Yes, connected universes. But, even then, so all the universes are connected. So while they're kind of parallel, coexisting realities, still they're, you could consider that as one big universe, the multiverse.
I have a question.
I was going to say, just go ahead, Johnny.
Yeah, I wanted to butt in and say, you mentioned that if something went straight up, it would just keep going for eternity. But I recently saw a video. It was on YouTube, and it was about a rocket, an amateur rocket that was launched. It was supposedly the biggest one of its size, and it was sent up 73 miles straight up. And as it took off, it started spinning very, very fast, almost like a bullet, and it was going very fast. And all of a sudden, as it sort of got to this height, it just come to an abrupt stop and stopped spinning. And I just wondered how that works, how we get out of space. And I wondered if you have any insight or knowledge on that.
Yeah, so, although we can't see it, it's like we're at the bottom of a well, in terms of the curvature of space-time around us. Actually, luckily, for us, it's not like a well, more like a valley. We're at the bottom of a valley. And, just as it takes energy, it takes exertion and time to move up that hill, to walk up that hill. Now, some things don't have enough energy to make it up the hill. So for our analogy, it's Mount Everest. We just don't have enough energy to make it to the top of that hill. And that's what happened to the rocket. It's fighting up that curved space-time, and it doesn't have enough energy, doesn't have enough momentum and speed, and it stops and rolls back down that curvature of space-time. And now that's one of the reasons why our chemical propelled rocketry is so primitive, because you're just trying to use a controlled explosion to overcome this geometry of space-time. There is an alternative, and that is to change the geometry of the space-time. So if it's like a hill, what if you were to, like you're at the bottom of a valley, what if you were to reverse that, so that it's like you're at the top of a hill, and you just keep making this hill that you roll down, and you keep doing that all the way up the hill. You use the same principle in the reverse manner. I know that's a little bit of a weird way to say it, but that would be essentially anti-gravity, gravitational control. So, instead of fighting against that geometry, you simply change the geometry.
I was just going to say, Johnny has another question for you. Go ahead, Johnny.
Yeah, sorry, it's another question. It comes from Pete in Cambodia again, and he's asking the same sort of question as Jose, which was, could you explain the chaos theory and give it a sort of a layman's terms explanation?
Yeah, so it's a interesting area because this happens time and again in science, because chaos theory is the study of order, the study of the dynamic and mechanics of order, but it deals with unpredictable systems. So from our perspective, it's chaos. It's chaotic because our ability, with our present day knowledge, or lack of knowledge, I should say, and technological capabilities, we cannot predict what's going to occur. We don't have that capability in many systems, and actually, this occurs very quickly. When you start talking about the movement of water, in a river, it becomes a chaotic system. It's unpredictable. So almost as soon as you start getting beyond like 3 molecules, in many instances, you're entering into chaos theory. It's been a source of confusion because it's caused some physicists and mathematicians to say, well, the universe, reality, is inherently unpredictable. That's quantum indeterminacy. It's inherently indeterminate, non-deterministic. And again, for me, that's a weird conclusion to come to. It's odd. Just because you can't predict something
doesn't mean it happens. Yeah.
Yeah, and they've come up with all these arguments that no, it's not because of our low technological ability for measurements or our lack of knowledge. It's just that it's inherently chaotic, and in some respects that is true. I mean, if you're looking at a subset of a system, it does behave as if it's inherently chaotic and unpredictable. But again, you got to look at the larger picture. If you looked at other ways that it's being influenced, it becomes less and less unpredictable. And at the larger scale of things are deterministic. Yeah.
Actually, I have a question I wanted to ask you. Then we have yet another question from a listener, which Johnny's going to ask you. Let me ask you this first. What are your feelings and thoughts about the particle colliders here on Earth that we've built, and CERN being the largest at the moment?
Well,
I mean, have they discovered anything that you didn't already theorize or others didn't already theorize?
Well, I don't think they're really discovering things. It's like it's good because whenever investigating, even if it's just blowing particles apart, you're going to learn something. I mean, it's not completely useless, let's say. And I'm also in favor of it just because it really does instill a lot of inspiration, gets people interested in science, which for me as a scientist is a good thing, even if it's a bunch of BS, what's being done, because, it goes back to erroneous ideas that your fundamental particles, your lepton, which are your quarks and electrons that make up your hadrons, your protons and neutrons, and which are your electrons, are zero-dimensional. That they're point particles, and since they're point particles, they can't have their own mass. So the only way, because they don't have any internal structure. So one way is say that they're strings, and their vibration is given the mass. Another way, which is through quantum field theory, is to say that there's another particle, a boson, the Higgs boson, that gives it mass when it interacts with it. And what they do is they say, well, this particle would have 126 giga electron volts. That's its energy, and so we'll take two protons and get them up to 99.9999% the speed of light, smash them together, and we'll see a piece fly off of it that is 126 giga electron volts, and we'll call that the Higgs boson.
Yes.
And we discovered it. We found it. It's there. This is how it works. Well, maybe. I mean, maybe I'm wrong.
Well, what about the statue? Okay, I do want to get to Johnny's question because he's been waiting, but I'm just going to ask you to quickly, briefly say your comments about the statue of Shiva in front of CERN.
Oh. Well, there's a good amount of physicists who aren't as square, as straight edge as the mainstream would prefer them to be, maybe even. But so within Hindu mythology, Shiva is like the destroyer, I believe. You got like Atman, who is the creator. You have the destroyer, and then the regenerative God aspect. But it's very apropos. I mean, they are the destroyer. In order to build their theory, they're smashing apart subatomic particles, protons in this case. So they understand. I believe it's just that it's kind of interesting. How they give it a kind of religious, almost mythological veneer. Kind of cool. I mean, a little bit of mysticism in there, and just like that religion describes it, destruction is just another part of the cycle of creation. So if they're gonna blow apart a couple of protons, it's not the end of the world.
Yes, people thought it would create a black hole and suck in the whole Earth. Anyway, let's turn it over to Johnny to ask the listener a question. Go ahead, Johnny.
Well, we've got a Facebook question from Gregory in Antwerp, Belgium, and he's asking on a similar lines, what do you know about DMT, the spirit molecules?
Yeah, so dimethyltryptamine, is a very important molecule in the sense that it's an entheogen, and this is a large class of molecules that have a great deal to teach us, not only about neuronal biology, but certainly the quantum mechanics of neuronal biology. But I'm sure that most people interested in DMT know, its basic description, a molecule that's produced naturally, that is to say endogenously, by the pineal gland, and when it interacts with the neurons, it can cause you to kind of relocate for a short amount of time, tune in to areas in which you're not normally tuning into. And so, as far as, my perspective on its phenomenal behavior is through quantum resonance, in that your brain, in many ways, is tuning into a very specific subset of the greater reality. So you're not perceiving everything that's going on around you. Far from it. We have a very limited window of what we're aware of in terms of the greater reality of things that are going on around us. The example that's so often given is of the electromagnetic spectrum, where, up until 100, 200 years ago, light, visible light, was the electromagnetic spectrum. But, come to find out, that is the smallest band of the electromagnetic spectrum. In fact, all around you, constantly, there are electromagnetic waves that you don't see, you don't perceive, you're unaware of them. And now that we are aware of them, we use them to completely revolutionize civilization. It transmits all of our communications, links the world together, the human civilization together, through its ability to transmit information, as well as, yeah.
Yeah, sorry, because you mentioned that, the pineal gland, and I see a lot of information about what they call the calcification of a pineal gland. Have you heard anything about this?
Yeah. So, naturally, or perhaps somewhat unnaturally, as a person ages, the pineal gland will calcify. And this has a small degree to do with things like diet and exercise. So actually, the amount that you can increase blood flow through the pineal gland, and having a diet low in like trans fatty acids and stuff like that will reduce or even completely mitigate or obviate calcification. But the pineal gland has naturally occurring calcite crystals, as well as other kind of microcrystalline structures around it. And this is extremely interesting because, so possibly, piezoelectric crystals that with physical vibrations will produce electrical currents, or through electrical currents will vibrate. These are naturally occurring around the pineal gland. And, it just so happens that you have extraretinal photoreceptors in the pineal gland. Inside it, you have rods and cones, light receptor cells, proteins, so it literally is a third eye. And in fact, there is practices, meditations, things you can do to activate, so to speak, and actually see light through your pineal gland. This was a major process of that the mystics and sages, yogis would go through. Tibetan monks, activating that light, coherent light emission, biophoton emission, activating the extraretinal pigment cells, photoreceptors in the pineal gland. And this is causing the microcrystals to vibrate, to emit electrical impulses through the brain. It causes the secretion of dimethyltryptamine as well as other entheogenic signaling neurotransmitters, so that is one way that you can tune into a greater awareness of the reality that you're in, that you occupy. Things that are going on around you that you're unaware of. You can open up the ability for telepathy, for communication with beings that you would think of as kind of in another dimension, these kind of things. That is, it very quickly goes into the mystics. Now, one of the things during my PhD thesis, my graduate work, I was studying the pineal gland and also associated structures. And I mean, the structure of this system is extraordinary. It's just fascinating. It's so you've got the pineal gland situated between the left and right ventricles, which are water-filled sacs, cavities at the center of the brain, at the center of the left and right hemisphere. Above them, you have the cerebral cortex. Now, the pineal gland sits kind of in like the commanding position, the commander position atop that, and it sends out these sinusoidal, kind of like undulating tissues down into the ventricles. These water-filled cavities. It's called the choroid plexus. Now, and this runs all through the central water system of the brain, the ventricular system, third ventricle, fourth ventricle, and this is the only structure that doesn't have a blood-brain barrier. So, and it's an extension of the pineal gland throughout the brain, and so it allows for the uninhibited passage of things into the body and from the body.
Forgive me for interrupting you. We have literally about 8 minutes or so left.
Okay.
I wanted to. We have a question, a listener question. I'm going to let Tom ask you. Go ahead, Tom.
Okay, yeah, we got a guy, his name is Jimmy in Smyrna, Delaware, and he wants to know what's the hottest area of science that you see right now? Where do you feel the hottest spot is in science right now here as we go into 2016?
Biophysics. This, to me, is one of the hottest areas because it's an emerging field where the quantum mechanics and even unified physics, quantum gravity, is being applied and described in the biological system. Being used to describe how memories form or awareness, and even metabolic processes. And one of the reasons why it's becoming so hot right now is because there's been experimental validation of these phenomenon, quantum mechanical phenomenon, in the biological system. The chloroplasts of plants, which are the photosynthetic centers, they employ a form of superconduction, quantum tunneling of electrons, where they get 100% efficiency in the transfer of electrons, so that when a photon strikes the pigments, the cytochromes of that macromolecular structure, it kicks an electron, a high energy electron up, maybe even transforms into a high energy electron. That molecular system is able to grab that electron and transmit it with 100% efficiency to the reaction center to make food. Carbohydrates, sugars. Now, this is showing, for one thing, the supreme technology of nature, of the biological system. It is. I don't want to say manipulating, but it's engineering. It's working with subatomic matter, photons and electrons, and it's doing it with quantum tunneling and superconduction, quantum entanglement. This has also been verified in the mitochondria, which are normally known as, or most commonly known as, the energy producing centers of all animals as well as plants. So within every cell of your body, there's up to 1,000 mitochondrial organelles, and they're all using quantum tunneling to supply you with the energy that drives every cellular and molecular process and keeps you alive. So it's a hot area, and you're seeing more and more talks given at very mainstream, conventional, academic institutions, and the number of publications on it has just skyrocketed. So it's a very, very hot area. Another pretty hot area, though, which is a little bit different, though, is in genetic engineering. There's been a revolution.
Well, isn't it true that they actually harvested some organs from Neanderthals? I read somewhere.
It wouldn't be organs.
Something. I wish someone out there can give me the link right now.
They definitely isolated DNA and sequenced some Neanderthal genome.
Okay.
But there wouldn't be any organs from the Neanderthals.
Just plain organs without them beings. Yeah.
Yeah.
I'd like to get to the bottom of the story. This was told by somebody. Anyway, go on.
I hope somebody can get the link, and I'd be interested to hear. But because with the isolation and sequencing of Neanderthal DNA, they were able to show that most Europeans have Neanderthal DNA. A small percentage of our genome in many individuals has Neanderthal DNA. So we're hybrids, which should come as no surprise. Humans are hybrid beings, but just in terms of this revolution in molecular biology that's occurred in the last 5 years, there's now the ability to very easily and cheaply modify the DNA of any organism, with a level of ease that has never been seen before. And so it's kind of an area that is transforming that science, and it's certainly going to have large ramifications for all of us.
We got just a couple of minutes, so I'm hoping in about a minute or two you could talk to us about how gravity affects time travel.
It can be used as a time machine. Mm-hmm. If you produce a strong gravitational field, it will transport you, in a sense, but really, it'll transport you into the future. You could actually make a literal time travel machine if you produce a strong gravitational field, somehow such that it doesn't crush you. You could jump 1,000, 5,000, 10,000 years into the future. And if you turned it off, turn it on, turn it off. So it is a time traveling machine. Now, that's a really strong gravitational field. If you were to go one step further and do kind of the opposite, where instead of doing a positive curvature of space-time, you did a negative curvature of space-time, which you can do with negative energy, negative mass. The electron has, in standard theory, it has infinite negative bare mass, infinite negative energy. But it's shielded by the quantum vacuum. There's all these photons, virtual photon pairs, and electrons and positrons popping in and out of the vacuum around the electron that makes it look like it has a small positive mass. But if you could get rid of that vacuum fluctuation around the electron, within standard theory, it would have a negative energy, a negative mass. So this could be used to give you a fairly large negative curvature of space-time. That is to say, anti-gravity. Now, if you got enough of it, you could open up a wormhole, and a macroscopic sized wormhole, something that you could step through. Now, if you were to open up one, it'd be actually kind of difficult not to open up one that already exists as a microscopic wormhole. You could jump backwards in time, and this is through gravity, because you're just talking about the curvature, the geometry of space-time. You're taking a little tunnel through space-time, opened up by negative gravity, anti-gravity, and jumping back to a different space-time coordinate, a different coordinate in time and space. So again, it can be used as a time machine, and it's there's many potential applications of that for time travel.
It's been an incredible opportunity to have you on the show. Of course, I want to thank you. I want to thank the Dr. J Radio Live team, starting with my co-host who stays up till 5 in the morning plus a.m. Greenwich Mean Time live in London. And, of course, Tom, my webmaster, and then some. But most importantly, it's you, the listeners. Real quick, I wanted you to plug in, Dr. Brown, your website again for everybody to hear.
Okay, yeah, but thank you, Tom, Johnny, and Dr. J, and thank you all the listeners. But my website, williambrown.scienceoflife.com. But if you want to get into some really interesting, entertaining stuff, the Resonance Academy .is, or even resonance.is, the Resonance Institute, which links to the Academy as well. There's lots of great material there, and with my colleague Nassim Harriman. And
that's right. Yes. Well, again, I'd like to thank you very much. Thank everybody who's been listening. Join us, of course, next week for some awesome guests. All you have to do is go to drjradiolive.com, drjradiolive.com. A lot of the shows are archived on YouTube. They will all end up being there at some point. We are working on them as fast as we can, but we got some really cool ones waiting for you to be fixed, and they will be up there very soon. The way you get to the YouTube channel is go through the website drjradiolive.com and just click on YouTube, or go to youtube.com/drjradiolive. And if you'd like to send me a tweet, use @drjradiolive. You could contact me through the website and everything else. Remember, every social media account is based on the name of the show, so that's the easiest way for you to remember. With that being said, let's hear some friends and, of course, guests of this show. And I am Dr. J, signing out for Dr. J Radio Live.
I'm Jack Osborne, and you're listening to Dr. J Radio Live.
This is George Tsoukalos, and you're listening to Dr. J Radio Live.